My name is David Szabo. I work for a startup called Virgil Security. And today I'm going to talk to you guys about end-to-end encryption, how this thing works, what is it, and I want to show you how fundamentally broken our app security is today. And there's nothing you can do about it with the tools and thinking on a level where we are thinking today. So I want to show you techniques, how WhatsApp did it, how other companies did it, how Twilio did it. And hopefully I can let you go at the end with some sample codes that you can use yourselves in your own apps. And because it's Google, I brought some Firebase samples today. How many of you guys are Firebase developers? Cool. So what entitles me to talk about security? My team built the Twilio's end-to-end encrypted chat. So if you are using Twilio, if you are transmitting messages end-to-end encrypted, that's our open source tech. That's the disclaimer. I'm pretty sure that you guys are all familiar with this workflow when you have a user and you are building an app, and then you log in your user with, let's say, OAuth or a username password authentication, and then your user decides to now do something in the app. And then he runs the database query. Let's say he wants to download some data in the app. And the flow, as how it happens, is it hits a REST API in your cloud, and then it goes to the backend and to the database to retrieve the data, and the data comes back to the app and you display it. But along the way, once the user has been authenticated, at every point in this workflow, there is an access check. What is an access check? It's these two lines of code. Like every stage in that journey, your app or your backend or your cloud service provider, your Google, your Firebase, your AWS, is doing access checks to see if your user with the token that you gave back to your user after login is allowed or should be allowed to access that resource. That's it. That access check is happening along the way, every step. So that access check is actually a piece of code that it's an if statement that compares two values, and if that returns true, then your user has access to the data, otherwise not. What kind of security is this? And it's really similar to how building security works today. You check in at the reception, you get a badge, and then that badge can open doors for you. And then when the door accepts a badge, it opens. If it doesn't, it doesn't. And then when your card expires, you're not allowed anywhere. It's cool, okay? It works in real life. But there are people who are not entering the main door. That's the problem. Some of your users will be entering from other doors, not on the main door. And you need to be prepared for that. And access checks like that are not going to stop them. I'll give you another example going back from real estate security into computers. How many of you guys have ever debugged a kernel? Unfortunately, I did. Oh, next speaker debugged the kernel before. So in the user mode, where our apps are spending most of their time on our computers, processes have fences, they have boundaries. Each process have their own memory block, their heap. You cannot access process 2's memory from process 1. It's protected. There's no way unless you build a bridge between the two processes and do something. But as soon as your code runs in kernel mode, it's all hell. It's all Wild West. Your code, your driver, or whatever runs in kernel mode will access every piece of memory for every process without control. That's the access check that your user mode switch does in your operating system. And this is the kernel mode that your hackers will see when they hack into your database. There is no protection against that, because your database, even if it's protected, the database file is encrypted in your cloud. Your database, your live database, is a live database. Anybody can query that who obtains a token to that database. Or whoever captures that database file and captures the key that is stored pretty close to the database file will also have access to the database file. So kernel mode is how your software, your app, your database looks like to an attacker when they hack into your app. And that's how every week 3-4 data breaches happen. Unlike in real buildings, the attacker is not entering on the main door. They attack from your database, they attack in your front ends. They come there, and that's where they breach out your database file. That's where they breach into your live database that is protected with a password that somehow gets out, or you accidentally make a mistake and data gets out. So there must be a better way. There's a little change in a slide. There's a key gonna show up in a phone. So to introduce keys in the client apps, and those keys encrypt data between users, letting your cloud database totally blind, not seeing the data. They're storing the encrypted data that you encrypt on the user devices, and they have no way of seeing it. So that's the only and the best way that I know today how WhatsApp does it and how other chat apps do it to protect user privacy. And I'm going to explain the details in a second. In summary, if you implement end-to-end encryption for your app, like how WhatsApp did it, your two users will be sharing data in your app. Could be chat messages, could be health records. HIPAA is a keyword that I mentioned today in my slides. So if you guys are in healthcare, in the business of healthcare, you'll appreciate that being HIPAA compliant is important for some companies. Encrypting data helps you be HIPAA compliant, but compliance is not the reason why we are doing this. It's the privacy of individuals, it's the users, it's the people's private data that we want to protect. So when these two guys are talking, chat messages or sharing a piece of document, then they encrypt it on the client devices or in the browsers, and then it's the encrypted data that makes it to Firebase, to AWS, or whatever cloud you guys are using. There's no way that the cloud providers will see your data. There's no way that anybody else will see your data besides those users that you want to access the data. It's cryptographically enforced. And the key point here is not as if Firebase was unsecure or Google's cloud or AWS was unsecure. Those are, I know a bit about Google Cloud Platform security. I know how their blobs are protected, all the key management. Google is doing a phenomenal job. The point here is if you're one developer who makes one mistake one day, with that one mistake you can breach out your entire database, like your million users' data. There shouldn't be a way for somebody with one mistake, with one password, with one data file dump to breach out everything. So there has to be a better way. Okay, I'm going to show you a real basic overview of how end-to-end encryption works in a chat app. So this is your infrastructure. You have a front-end server, and you have a database server, and then you have your app where two users will be chatting. This is how HTTPS works. When the data comes from the mobile app to your front end, again, played back, it's secure over the wire, and then it terminates on the front end, on the REST server. Whoever is sitting there, whatever log files are captured there, whatever is happening in that server's memory, and a bunch of other things can happen, it's been secure up to that point, but now it's there in the memory. And then, as it goes into your database, it gets re-encrypted again. HTTPS goes and decrypts, like terminates traffic again on the database server, where it gets written into the database, into the live database. And typically, the database is encrypted with a key. The database file, as it is on disk, is encrypted with a key. In Google's example, with multiple keys, like they encrypt things with like blocks of blobs instead of the entire database file with a single key. But the point being is that key there remains, because the database service will need access to that key in order to read up the file. I know, that's the problem. Whoever gets into that database, they can capture that file, and with that file they can decrypt the database file. Or if they hack into the live database by knowing your password, your account password somehow, they have access to every user's data without even looking for that key. So that's how it works today. And I'm not blaming Google or anybody for this. This is how the internet was built. This is the security today. So how does end-to-end encryption works? Real simply. You have your chat app, and now we have a key on the device. We decide that we want to protect this chat thread with a key. That key will encrypt that message, and it will be the encrypted message that will go with HTTPS on the front end. And because it was encrypted on the client device and the client still has the key, it's not going to be visible for the front end. And then it keeps going into the database, and it gets written into the database, and it remains encrypted. And then, so it's a piece of encrypted data, an encrypted message that the database will store. And when the user on the other side downloads that encrypted message, the user will also have a key to decrypt it with. So in other words, Firebase or your cloud database or your on-premise database will never be able to decrypt the messages because the end users hold those keys. And I'm sure that you have a million questions. What happens to those keys? Where do they come from? How do they back up? There are answers for everything. And then we try to keep it simple. To give you one step further, do you guys know how private-public keys work? So just a little refresher. The way private-public asymmetric cryptography works is you have a public key, you as a user have a public key and a private key. You give out your public key to all the other users so that they can encrypt data with it for you. And then when that encrypted data arrives, your private key will decrypt it. Make sense? So your public key is public for everybody. And your private key is with you on your device. You have to hold on to it. You have to keep it in your pocket real safe, because that's the thing that decrypts the piece of data. Now, those public keys needs to be available in some cloud. And that's a piece of service that if you sign up for a free account with us, you guys get. You can publish your public keys. Or if you don't want to use a service like us, you can just build your own public key store, store them in your database. It's public information. And then when the user wants to decrypt a message, when you encrypt a message, you use that other user's public key to encrypt the message with. And when that other user receives the data, they use their private key to decrypt it. This is the simplest scenario. And then we are actually building a book of key management right now. We learned our ways from Apple, how they built your Apple device's keychain and iCloud. There's so many really cool patterns and practices how you can chain keys together to build group chat when you have multiple participants in a chat or multiple participants in a document library, how you can encrypt data in a way that you don't have to re-encrypt everything when a new user joins in. So we are blogging about all those things. If you guys are interested, follow us on our blog, and we'll teach you, we'll show you how to build your own keychain, how to build your own multi-device management experience. So let me show you how an app like this works in action. This is the new Firestore. This is the Firebase dashboard here in the middle. And I'm just going to make this. So I have two apps. This is Xcode, two iPhones. I have an iPhone X on the left, which is a person who listens to a name, Alice, 31. And then I have the mysterious other person who is called Bob, 61. So two users with two apps, with the same app on two phones. And then they have chat threads. Technically, I need to log out here. Here's my Firebase. I'm going to just maximize this for a second. Here are my channels that are end-to-end encrypted, and I'm going to try to find these two, Alice 31 and Bob 61. Give me a second. If you see those two, then shout. This is the Firestore database that is storing all the chat threads between the two users. Yeah, here it is. Thank you. And then I click here and I see the messages. Let me wait for a new message to be sent. Alice is going to send a message to Bob to say, "All good, my dear." And suddenly a new message pops up. I love how reactive the Firebase dashboard is. Let me see that message here. Oh, that's a weird message. Let me put it into text edit and make it a little larger. As you would expect, it's encrypted. Let me send another message again, the same message. All good, my dear. Period, period, period. Okay, a new message, number 3, just showed up. So here's 3. Let me take another copy of it. So you would expect, if I send the same message, this has to be the same, right? the crypto that we have built into those samples is non-deterministic. You cannot tell whether those two users are speaking about the same thing. Why is this important? What if Bob is waiting for one particular answer from Alice to start something? Or what if you know what Bob asked and you want to know if Alice said yes or no to it, and then you already captured a yes previously, and if it repeats, then her answer was yes, and now you won the case. No, with non-deterministic crypto, you cannot do that. The same message is going to be different. It's going to be different every single time. You cannot trace it back. So this is how it looks like, and then as soon as I sign in with Bob61 again, and I'll explain why I logged out, those encrypted messages will be delivered seamlessly to the end users. Yes?
So all you've encrypted is just the message. Just the who it's from, who it's to, the time it was sent, everything that database does. Not send it to clear, but it's sent to HTTPS.
Yes, yes. And you can choose. You can decide what you want to crunch on your server, or what you want to partially encrypt or fully encrypt. So it's not the silver bullet to everything. Sure. But the data, for most developers and most companies, the data that they don't need is what gets them into trouble when it breaches out. And why don't you protect it so that it doesn't get you into trouble? There's one more thing in this sample, and this is the part where I want to speak about. Security and compliance sometimes come hand in hand because some companies do security for the sake of compliancy so that they meet HIPAA standards and FERPA and all that good stuff. So in this sample, as soon as messages are delivered, we delete the messages from Firestore. So if you go back here, you see the body has been deleted. I'm going to send another message, and you see message number 4. Oops, already deleted because it's been delivered. HIPAA allows you to be, your company to be, or your app to be exempt from HIPAA if you are only delivering messages in an encrypted fashion like UPS delivers your mail. So this is how our sample that you guys can play with for Firebase have met HIPAA's requirements for Firebase if you're building chat apps, like chat that doesn't have permanent data but just message delivery from one user to another. This is a HIPAA compliant chat app on Firebase. So if you guys are in healthcare and you're building healthcare chat, it's done. Any questions?
Repeat this point, I'm sorry. Could you please repeat this point, this use case?
Yes. So in this, the way these sample apps have been built is as soon as messages have been delivered to all users, they are deleted from the server. This is how how the sample meets HIPAA's conduit exception requirements. Yeah, we have a white paper on that. Yes.
Assuming that you don't want to delete some of the data that you have encrypted, so how do you deal with searching the data?
No, you can't. There are many attempts to do searchable encryption, and we in one of my past startups, we built a prototype on it. It's very limited. The problem with searchable encryption, it's possible, but the factor of how much the index grows, if you have a kilobyte of data and you have a terabyte of index, at one point it's not worth it. You better just ask the user to download everything on a client device and do some search there. So the golden rule for end-to-end encryption, and this field is so new, even though it's in every chat app, is only encrypt stuff that you don't need to crunch on, only encrypt stuff that can get you into trouble. If you have stuff that you need to crunch on, like social security number on your server, encrypt it, encrypt the first digits and leave the last four out. Or if you have date of birth, encrypt everything but the year. If you have names, encrypt them. If you have chats or doctor's notes or privacy stuff that you don't need to index, encrypt them. And if you take your app and build it end-to-end encrypted and you ask your customers, what would you choose? Would you like your data to be private, secure, or would you choose it to this particular thing to be searchable? Most of them, I assume, would say, you know what, I would choose privacy, especially if you are if your customers are enterprises. And that's how Facebook did it really, and Google did it really smartly with Allo. that they enable users to switch between secure and not secure. And then they understand if it's not secure, it's going to be, there are going to be more features. If it's secure, there are going to be less features, but it's my privacy.
Or they can search whatever data that
Yeah.
you just need to add a find functionality there.
Yeah. You can search on the client side. You can do some guess search on the server to only transfer data to the client that is already a subset of the data, and you do the crunching on the client side. So you can do all sorts of tricks. But at one point, if you guys decide to build end-to-end encrypted apps, don't try to compare it in your minds with a normal app. It's more. It's a lot more. And you have more constraints, but at the end of the day, you get something that is unbreakable. Yeah. I have 3 steps for you guys to start building end-to-end encrypted apps, like trying to simplify it to 3 steps. The first one is create keys for every user. If these are the Lego building blocks of how to build your X-Wing, this is how it starts. Create private and public keys for your users. So when your users sign up, create a private key in the browser or on the device. We have totally free SDKs to do it in JavaScript, in browser, in iOS, and Android. Create one private key, Virgil.generate key. That's it. And then generate the public key of that private key and publish it in either our cloud or your own database to make it available for users to find each other. Once you have that, you're like 50% there. You have the solid foundation to build secure apps. Step number 2, start encrypting stuff. So if you have some sensitive data, this guy taking a selfie, encrypt it at the moment when the selfie has been made, or uploads a document, sends a message, or anything. Encrypt it immediately. If it's sensitive, encrypt it on a mobile app, and you have to know who that message is for or who that data is for, so you need to encrypt it for that person. If you don't know who that data is for, we have multiple ways of dealing with that situation. Briefly, you can create a key for that folder or for that selfie or for your old photos, and then leave that key. And when you want to share it later, you can encrypt that key that decrypts the content with the user's public keys. So you can encrypt keys as well. I'm constantly blogging about key management techniques and how you can do that and how Apple did it, because they already built a way. They just didn't open source it, unfortunately. So we are technically building iCloud and Keychain for you guys that you can use in your own apps. In summary, encrypt stuff in the app. So once you have the basic foundation, every user has public, private keys, encrypt data, sensitive data in the app. So here's an example. You take a selfie, you will create an encrypted version of that selfie by just encrypting it for one of your users using their public keys. And now you have an encrypted data, and that's the data that you store in your database. That's it. Is it difficult? Not really. And then the third one is what happens if a user is losing the device or is changing browsers to another one from where the user private key was created at registration time. And this is a problem that the world couldn't deal with for a long time. When a user signs up, you create a private key for that user, the brand new user private key, and you capture a password from the user. We derive a key from that password. That's what we call a brain key. There's the logo. And that password key, you'll encrypt the user's private key with that password key, and then store it in the cloud. So let's play it back login time. Next time, when the user logs in from a new device, the user types in the password, gets the same password key, downloads the encrypted user key from the cloud, and that password key decrypts it, and you have the user key. This is how we deal with lost keys on devices. Make sense? We have a key that lives in the user's brain. That's why we have that ugly logo that is a key with inside the brain. But we have the user's password that is the actual key and is strong enough. Yes, question?
What happens if I change my password?
So if you change your password, you need to know your old password. So you create a new brain key, and you encrypt the user private key with that new brain key, and now you have a new, you store a new version of that encrypted
As an
key.
application developer, I
re-encrypt only that user key. Because that user key has not changed. A brain key is just a way to get your private key, your user. And we have multiple techniques. If you forget your password, we have multiple ways of unlocking that information. Yes? So this is full circle now. This is full circle now because it works like Apple's keychain. When you log into your Apple device, you can log in with your Face ID, with your Touch ID, with your PIN number, with your Apple ID password. All those are deriving keys that decrypt your keychain that has all your secrets on your iPhone or in iCloud. With this stuff, you can do the same thing. You log in with a password, you get a key, you get your user key, and then you decrypt all your communications with your user key or all your documents. So it's a full circle. You cannot hack a user unless you know that user's password. And this way of storing passwords is not hackable because the private key is not living anywhere. It's in the user's brain. Anyway, so that's my long rant of the 3 steps. So create keys for your users, encrypt stuff as they come in, sensitive stuff, and make sure that your keys, you have a solution when your user keys are lost. That's a way to do it. Once you have those 3 foundational components in place, you can build WhatsApp. These are the URLs. All start with GitHub/Virgil Security, demo Firebase iOS, demo Firebase Android, and demo Firebase JavaScript, JS. This thing works in a browser without add-ins. It works anywhere and everywhere. Any questions? Any remaining questions? Yes. How do we protect ourselves? We actually have our own tech. So we are using our own tech to protect your API keys. And we are open source. Open source samples, open source SDKs, so no backdoors for sure. What is the complexity requirements for the brain key password? It's as complex as you set it. The key, the string that we use to derive the key is an app ID, a username, and a password concatenated into one string. But given that we don't store a copy of that private key anywhere, nobody can brute force it. It's a thing that you cannot catch because it lives in your user brain. It gets created every login time on the client device, and it gets destroyed. So it's something that is non-brute forceable. Brute forcing needs the thing that you want to brute force exist. So all you can do is guess the passwords. We always recommend complex passwords, by the way, so don't do password 123. With that, thank you so much, everybody. I hope that I was entertaining enough and I showed you a brand new way of building secure apps. Thank you.